Welcome back. Let's move on and keep rolling. So the next one is week 6, number 6, binary tree right side view. All right, so given the root of the binary tree, imagine yourself standing on the right side of it. Return the values of the nodes you can see ordered from top to bottom. All right, so I guess it's pretty clear that what matters is the levels, right? Ordered from top to bottom. This is going to be a breadth first search and not a depth first search, right? I think that hopefully it's pretty clear from the picture that we can see here that this is a breadth first search. Now, you can imagine in an interview you might get a variation of this. You might get a left side view, right? It goes this way instead. Hopefully you don't get top side view because I'm not sure how to do that one. You'd have to figure out the balancing. But right side view looks fairly straightforward, right? Imagine if you could split these up by levels, right? Breadths. Here's one level. Here's two levels. Here's three levels. And imagine I gave you these lists, right, of levels, and you had to figure out what's the right side view. Well, if you're given this list, call this list 1, list 2, and list 3, all you'd have to do is return list 1, -1, list 2, -1, list 2, negative, or list 3, -1, and you would have the right side view of all of these, right? So when you're thinking about the code, we're just thinking about how to create these lists, right? So let's say you had a results array here and you wanted to do a breadth first search. You would do BFS, and then for each level you would results append whatever's at that level at -1, right? If there is a level. So if there's a level here, then results append, right? And then that's really the crux of it. And we know how to do BFS, and it requires typically some idea of what we want to process, right? So to process, let's say it's a list, right? And the list starts with the root, right? We want to process this root, and while toProcess has any elements, then we, consider the next child or the next children is some array here, right? And then we process all of these elements, right? So let's just make a copy here to process dot copy, and then for L in copy, right? If L dot left, next children, append to it basically, right? Append to here, and then if L dot right, append to here, right? That's the next children, and then toProcess equals our copy, right? And we also want to, if we had a results array, take whatever is in this current toProcess before we do that, and say toProcess -1, we want to append that to the results array. Hopefully it's representative that this pseudocode that I wrote here is this pseudocode that I wrote here, right? And in the levels, toProcess starts as this level, right? And then as we add the left and the right, toProcess becomes this level. And then as we add the left to the right, toProcess becomes this level. And, so on. So this is basically what we're going to code, right? We're going to code a BFS, pretty vanilla style. So if you want, you can code the BFS without doing anything yet, and it'll give you a sense of what to do, right? So let's say toProcess here is start to the root, and while toProcess has any elements, then we're going to make a copy here, and that's toProcess.copy, so we don't destroy what we have, and then for these elements, we're going to process them, right? We have a next to process. I'm going to have that be empty, and if the element that, has a dot left, right? So if it's not none, next to process, I'm going to append this L dot left, and I'm going to move this so we can see both the that I drew and this right here, right? So if L dot right is not none, then next to process append L to the right. And then we append to results. I'm not going to do that yet. And reassign to process. And then here, I'm going to return results, right? So results is going to start as an empty list. And all I want to do right now is show you what process looks like in various stages, right? So hopefully the test case has the example that they have here, and okay, so L dot val for L in to process. Okay, so in the beginning it starts as 1, right? Perfect. And we're creating a next to process. We're going to copy, and we have to reassign here. So to process equals next to process, and that's going to be the children. And yeah, I guess printing this isn't I didn't expect that one. I didn't expect the root to be empty. So if root is none, just return an empty list, I guess. Okay, great. So I'm just showing you the levels, right? So this is level 1, this is level 2, and this is level 3, right? And that's case 1. So you can see that to process, it's that -1 that we talked about here before. This holds what we want to have in the results array, right? This right here is what we want to put into the results array, right? So all that just to show you that that's how it's done. And this is a general breadth first search. We could have been doing some other logic. Imagine if we wanted to push the left one. Imagine if we wanted to push the second element from the left or the second element from the right, something like that, right? So I'm going to go to results, and we're going to append this to process, right, at that -1, right? So what are we going to append here? I'm realizing that we are putting the nodes here, so we actually have to do -1 dot val. Okay, so to process is the 1, it's the 2, it's the 2, 3, and then it's the 5, 4. And what we're outputting is that right side view, that -1 index of this 1, this 3, and this 4. Perfect. So we can get rid of that print, see what cases we may be missing. Not missing any cases. Perfect. Decent runtime. What is the runtime? Well, we only process everything once, right? So this is O of n. If n is the number of nodes. Now, is there any optimizations we can do? We got called out on this one. Turns out that, node is, if root is going to be none, we just want to return the empty list. We're creating results here. We're creating a to process kind of array. we're going to continue while we're doing the to process. Now, this is an O of n operation. Well, it's not O of n, it's O of whatever was in process. So we're copying. So could we continue this without copying? Now, copying is actually easiest, I think, to visualize mentally. Could we do it without copying? Let's think about it. Two processes. The next two processes here. So all we're doing is so what we could have done, if we really wanted to optimize this, possibly, I'm not sure if it would totally work, is we can keep an index, and instead of overwriting to process, we use the index as a sort of pointer to what would be the rightmost, right? So here, when I is 0, the rightmost is at 0.0, right, this root. And when we're doing element and copy right here, we can count what becomes the index at that point, right? So how would we do that? So we would save a, we honestly have to start from scratch. Let's just comment that out. What is the while loop even? So the while loop would be, I guess, I minus maybe it would be the same. I'm not sure, but maybe it would be the same. The next two process we wouldn't need, the copy we wouldn't need. We're going to iterate over I guess it would be this, last index. So we're going to iterate over for I guess we need a first index as well. Yeah, so I maybe wouldn't suggest trying this for the first time in the interview because it's a little bit confusing. So we're going to go from first index to last index. And we're going to keep an offset, I guess. And an offset is going to let us know what to change first index and last index to. It's going to start as 0. And for to process at I, that's going to be some current element that we're processing. And if cur left is not none, then we're going to append to this, right? So to process append cur.left. If cur right is not none, to process append cur.right. I guess we should add to this offset plus equals 1, and this offset as well plus equals 1. And then the new last index changes now, right? So let's take this example right here where we have 1, where this is index 1, and then we added 2, right? We added this left and then this right, so it would be plus 2. So 0 plus 2 would be 0, 1, 2. So that would be the index of the last index, right? So the last index would equal, I guess, whatever the last index was before plus this offset, right? And the results would append to process whatever was at this offset, right? Whatever's at this new last index. And we just continue, I guess. I don't know what first index does at this point. So first index, you'd want to iterate over whatever the last index was plus 1. So let's see. The first index would be whatever the last index was plus 1. And really you want the first index. Okay, so the trouble with this is we don't know how many nodes completely exist. So because we don't know how many nodes exist, I guess we're not sure when to break. It seems like maybe when to break is if offset is 0. Because that means that we've processed 0 new children. So yeah, maybe that's when you break. And then if offset is not 0, I kind of regret going down this path because I've never done this before, but so first index is last index plus 1. Okay, so when we get to the second level, it's going to be 0 plus 1, it's going to be 1, and then the last index will be whatever the last index was plus the offset, right? So it's going to be the last index of 0, it's going to be 2, so it's going to be 1, 2. We're going to go from 1 to 2 in this situation. So this should actually be plus 1. And then on and then on the next level, we're going to start from 1, 2, and then we're going to append 5 and 4, and then that's going to be 2 plus 2, it's going to be 4, and we're going to keep going. Okay, let's try this. See if this works. Invalid index. So it should be something like that. So we're not returning results. And just like before, we're not doing .val. Okay, perfect. So we are doing something, which is cool. So what we want is to actually append at this point, because we're missing that first one. Cannot access local variable last index where it's not associated with the value. That's true. So what we want is just this at last index, and then last index is plus equals this offset. All right, so cool. We did not improve on runtime. I don't know if that was worth it. That big detour there. Yeah, we somehow did not improve on runtime. I thought this would improve on runtime because we're using these pointers instead of what we did before. I greatly regret doing this and wasting everybody's time, but hopefully you saw some of the process and can verify that this is a horrible path to take during an interview. So this is your lesson now. Do not try something novel in the middle of the interview. There's a tried and true way to do this. It's right here. You just make the copy and then you iterate over the copy, right? It's a copy, so you can destroy, you can mutate it as much as you want, you can go through it, and then you could append to something else, this next process, and then your life is going to be so much better. Do not do something unnecessarily hard for truly no benefit in runtime. Thank you so much. This is, which problem is this? Binary tree right side view. Hopefully some of this was useful, not the last 10 minutes. And I will see you on the next one.